Hi guys, have you ever wondered how to perform mesh analysis in a network consisting of dependent sources? How to write KV allocation of a mesh that is having dependent sources? What are the things to be considered for avoiding mistakes while writing KV allocation of that mesh? Well, if you don't know those things, stay tuned to this session as I'm going to share how to find solution of a network consisting of dependent sources. Don't get confused, keep watching this session. It's me Abhisha, you're watching me on our channel Crack Easy, the place to learn how to crack easy exams. If you don't know the basics of mesh analysis, please do watch my session all about mesh analysis. The link of that session is given in the description box. I think we can start today's session now. First of all, I would like to ask you something. As I told you earlier, in this session we are going to learn how to perform mesh analysis in a network consisting of dependent sources. Do you know what is a dependent source? Any idea? Alright, in dependent sources, the source quantity such as voltage or current is controlled by another voltage or current that is defined at some other location in the network being analyzed. Got it? In other words, we can say that dependent sources are the sources where the source quantity is dependent on another voltage or current. Now, have a look at 4 types of dependent sources. The first one, current controlled current source. Dependent sources are represented by diamond symbols. You can see the symbol of a current controlled current dependent source here. The source quantity is defined as K into Ix, where K is a dimensionless constant and Ix is the controlling current that is defined at some other location in the network. Thus, here we have a current source that is controlled by another current. That's why it is called as current controlled current source. Got it? Next we have voltage controlled voltage source. This is the simple K into Vx is the source quantity where K is the constant and Vx is the controlling voltage which is defined at some other location in the network. Therefore, here we have a voltage source that is controlled by another voltage in the network. That's why it is known as voltage controlled voltage source. After that, voltage controlled current source. This is the simple G into Vx is the source quantity. Now can anybody tell me what would be G? G is a constant. What about this Vx? Vx is the controlling voltage that is defined as some other location. Finally, we have current controlled voltage source. This is the simple and R into Ix is the source quantity where R is a constant and Ix is the controlling current that is defined at some other location in the network. Thus, here we have a voltage source that is controlled by a current. That's all I want to say about dependent sources. I think it is better to understand how to perform mesh analysis in a network consisting of dependent sources with the help of problems. So let's move ahead and solve some problems. Find the value of dependent source in the figure. This is the network. Now you look at this network. Can you identify all the dependent sources present in the network? How many dependent sources are there? Is it a dependent source? No, it is an independent voltage source. What about this? Is it a dependent source? Yes, of course, it is a dependent source. Do you know the type of this dependent source? It is a current controlled voltage source where the controlling variable I is defined here. Now we are going to perform mesh analysis in this network. As you know, for performing mesh analysis, first we have to make sure it's a planar network. How we can check whether it is a planar network or not? Do you remember? A network is said to be planar if there is no crossovers present in the network. Is there any crossovers? No. So it is a planar network and we can use mesh analysis to find its solution. Our next task is to identify all meshes present in the network. When we scrutinize this network, it is clear that there is only one mesh and the mesh current I is already defined in the question. So next we are going to mark polarities of voltage drop across each resistor. Current entering terminal of a resistor should be marked as positive polarity of the voltage developed by that current. Here you can see this current I enters 2 ohm at this point. So we mark it as positive and this as negative. Current I enters 1 ohm at this point. So we mark it as positive and other terminal as negative. Next we are supposed to write KVL equation for this particular loop. Starting at this point in clockwise direction, first we observe this 5 volt voltage source with the polarity mark in the order minus plus. So we start our KVL equation with -5. Then the voltage drop across this 2 ohm. I is the current flowing through this 2 ohm. Hence the voltage drop across it can be mathematically expressed as 2 into I, and based on the polarity mark we add a term 2 into I to our KVL equation. After that, this dependent source 2I with the polarity mark in the order minus plus. So what term should we add to KVL equation to represent this voltage drop? We should add minus 2I. Finally, the voltage drop across this 1 ohm, which is nothing but 1 into I, and based on polarity mark we add a term 1 into I to KVL equation. Now this expression represents algebraic sum of voltages around this mesh. By KVL, it is equal to 0. Clear? When we rearrange this equation, we get I is equal to 5 amperes. In our question, we are asked to find out value of dependent source, that is 2I. When we substitute I is equal to 5, we get value of dependent source as 2 into 5, that is equal to 10 volts. Got it? Do you want to practice one more problem? It will definitely help you to get a more clear picture of mesh analysis, isn't it? So let's go for next question. Determine current I1 in the circuit. This is the network. Here we have two independent voltage sources, this 5 volt source and this 3 volt source, and one dependent voltage source 2Vx, where the controlling variable Vx is defined as voltage across this 4 ohm resistor. I1 is marked as current through this part of network, which is the quantity to be calculated. Since there is no crossovers present in the network, it's a planar network and we can use mesh analysis to find its solution. What is our next task? Any guess? Next, we are supposed to find out all meshes present in the network. When we scrutinize it, we can see there are two meshes. Consider this as first mesh and this as second mesh. Let us label I1 as mesh current in first mesh in clockwise direction and I2 as mesh current in second mesh in clockwise direction. Here, I1 is already defined in the question. That's why I selected this as mesh 1. Got it? Next, we are supposed to mark polarities of voltage drop across each resistor. First, you look at this 2 ohm resistor. Current I1 enters 2 ohm at this point. So we mark this point as positive polarity and this point as negative polarity. Current I1 enters 4 ohm at this point. So we mark it as positive and it as negative. Now focus on current I2. Current I2 enters this 4 ohm resistor at this point. Hence we mark it as positive and other terminal as negative. And the same current I2 enters this 4 ohm resistor at this point. So we mark it as positive and this as negative. So this is the network and we are going to write KVL equation in these two meshes. First, look at this first mesh. Starting at this point, first we observe the voltage drop across this 4 ohm. There is an interesting point regarding this 4 ohm resistor. It is common to both meshes. Hence, the current through this 4 ohm should be taken as algebraic sum of these two mesh currents. Here, I1 flows through this 4 ohm from bottom to top. On the other hand, current I2 flows through 4 ohm from top to bottom. Correspondingly, the total current through this 4 ohm can be taken as I1 minus I2 since we are writing KVL in first mesh, and a voltage drop I1 minus I2 into 4 is added to our KVL equation. Then the voltage drop across this 2 ohm, which is nothing but 2I1. Finally, this 3 volt source with polarity mark in the order plus minus. Hence, we add plus 3 to our KVL, that is equal to 0. It is written here 2I1 plus 3 plus 4 into I1 minus I2 is equal to 0. By rearranging it, we get 6I1 minus 4I2 is equal to minus 3, which is labeled as equation number 1. Next, we are going to write KVL equation in second mesh. Starting at this point in clockwise direction, first we observe this 5 volt source with the polarity mark in the order minus plus. Hence, we can start our KVL equation with minus 5. Then this dependent source 2Vx with polarity mark in the order minus plus. Correspondingly, we add a term to minus 2Vx to our KVL equation. After that, the voltage drop across this common resistor 4 ohm. Since we are writing KVL in second mesh, the total current through this 4 ohm should be taken as I2 minus I1. Correspondingly, a voltage drop 4 into I2 minus I1 is added to our KVL equation. Finally, the voltage drop across this 4 ohm, which is nothing but 4 into I2, that is equal to 0. It is written here. By rearranging it, we get minus 4I1 plus 8I2 minus 2Vx is equal to 5. That is labeled as equation number 2. Now you look at this dependent source. Here the controlling variable Vx is defined as voltage drop across this common resistor 4 ohm with the polarity mark positive at top and negative at the bottom. Hence, this Vx can be written as I2 minus I1 into 4. Vx is equal to 4 into I2 minus I1. By rearranging it, we get minus 4I1 plus 4I2 minus Vx is equal to 0. That is labeled as equation number 3. Thus, we got 3 equations and 3 unknowns. When we solve these 3 equations, we get the value of I1 as 1.25 amperes, I2 as 2.625 amperes and Vx as 5.5 amperes. Hope you remember in the question we are asked to find out value of current I1 and we got it as 1.25 amperes. Alright, so with this I'm going to close this session. In the end, one more thing I would like to add. Please try to practice more problems based on mesh analysis. It will definitely help you to perform better in upcoming competitive exams. Alright, great. Thank you so much for being with me. Hope you all enjoyed this session. Thank you.